morning, everyone. My name is Yuan. I'm from Johns Hopkins University. Today, I will introduce our work on bidirectional synthesis of pre- and post-contrast MRI by guided feature disentanglement. First, I would like to introduce the background of this work. In the area of medical imaging, unlike imaging techniques such as CTs and X-rays, MRIs can involve the use of gadolinium-based contrast agents, or GBCAs, to enhance the visibility of lesions, tumors, inflammation, and blood vessels. While GBCAs are generally considered safe, side effects and allergy may occur due to the contrast injection. Meanwhile, in clinical practice, there are cases where only post-contrast MRI is required due to the time and cost of acquiring additional scans. Thus, pipelines and methods designed for pre-contrast MRIs may fail in this case. This is an example of paired pre-contrast T1 and post-contrast T1 of the same subject. Our goal is first to simulate post-contrast MRIs from pre-contrast MRIs. This is to reduce or avoid the use of gadolinium without compromising diagnostic ability. While works have been done in this area, we would like to further improve the performance of current methods and also provide a more interpretable result. We would also like to explore an under-investigated problem, which is to simulate pre-contrast MRIs from post-contrast MRIs, so that pipelines and methods designed for pre-contrast MRIs can still be used when we only have post-contrast MRIs available. Combining those two goals, we would like to perform a bidirectional synthesis using a single model. In this work, we propose a bidirectional contrast enhancement prediction and synthesis, or BICEPS model, which can perform both directional synthesis using a single model. The BICEPS model takes 4 channels of 3D inputs, which are pre-contrast T1, post-contrast T1, T2, and flare. The BICEPS model disentangles contrast and image features while a feature encoder and generates a corresponding contrast enhancement map and a post-contrast T1 weighted image while the feature decoder. When our goal is to synthesize a post-contrast T1 weighted image, we will replace a corresponding post-contrast T1 weighted input channel with 0 images. When our goal is to synthesize a pre-contrast T1 weighted image, we will replace the input pre-contrast T1 weighted input channel with 0 images. We further allow the missing tissue contrast input by randomly replacing the T2 weighted image with 0 images, or replacing the flare image with 0 images, or both of them with 0 images during the training, which we call a input dropout. The training of the BICEPS model is done by applying the supervised loss on the synthesized pre-contrast T1 weighted image and the post-contrast T1 weighted image. Regardless of the input to the encoder network, it will always output a contrast embedding and an image embedding. The decoder network then takes the contrast and image embeddings learned from the encoder and generates a contrast enhancement map and a post-contrast MR image. Inside the decoder network, we design a contrast-aware synthesis block. The contrast and image features are fused together in the contrast-aware synthesis block while a sequence of learnable layers. We conduct experiments on a multiple sclerosis dataset, which contains 59 subjects. All scans were collected on a Philips 3T scanner. Each subject has a paired 3D pre- and post-contrast T1 weighted image, a 2D flare image, and a 2D T2 weighted images. Among 59 subjects, 40 were randomly chosen for training, 6 for validation, and 13 subjects for testing. To prove the effectiveness of our method, we compare with several baseline methods, including a 2D UNet, a 2D conditional GAN, which is basically a pix-to-pix model, and a 3D GANnet model. All baselines were designed for unidirectional contrast synthesis, so we have to train baselines separately twice for two-directional, while our method only needs to be trained once for both directions. Now let's take a look at the pre-to-post contrast synthesis result. On the left column is the pre-contrast T1 weighted image, which is the input to our model. On the right column is the real post-contrast T1 weighted image, which is the target of our model. The middle 4 columns here are the synthetic post-contrast T1 from different models. We can see that UNet and conditional GAN all fail to capture the detailed contrast enhancement of the synthetic post-contrast T1 weighted image. While the GANnet generally performed well, it was only designed for unidirectional synthesis, while our model can perform both directional synthesis. More importantly, we can directly synthesize the explicit contrast enhancement map and provide a more interpretable generation process. In the post-to-pre-contrast synthesis experiment, we further validate the clinical usefulness of the synthetic pre-contrast T1 using some downstream tasks. More specifically, we ran a slant whole brain segmentation algorithm which was trained on pre-contrast MRIs on all the synthetic pre-contrast T1 weighted image. Here are some qualitative experimental results of the post-to-pre-contrast synthesis. On the left is the input post-contrast T1 weighted image, and on the right is the ground truth or real pre-contrast T1 weighted image. On the middle are results from different models. The second row here is a slant segmentation result from different images. By comparing slant segmentation results from different models, especially between our model and the input post-contrast T1 weighted images, we can see that pre-contrast T1 generated from our model has a segmentation result that agrees more with the real pre-contrast T1 weighted image. This further proves the feasibility of applying our synthetic T1 weighted image to different downstream tasks. Here are some quantitative comparisons between different methods in both directional synthesis. In the pre-to-post contrast synthesis experiment, our proposed biceps model outperformed all baseline models in terms of both the SSIM and PSNR metrics. In the post-to-pre-contrast experiment, although our biceps model did not achieve the best performance in terms of PSNR, we calculate a more important metric, which is the dice coefficient of the slant segmentation result between the synthetic pre-contrast T1 and the real pre-contrast T1. We can see that our biceps model achieves the best dice coefficient among all methods, which proves the clinical usefulness of the synthetic pre-contrast T1. To allow the missing contrast input within our model, we further experiment with using only T1 weighted images or T1 weighted images with T2 or FLAIR as input to the model. In the pre-to-post contrast experiment, we can see that all inputs seem to be critical for the synthesis of the post-contrast T1 images. However, in the post-to-pre-contrast experiment, we can see that the T2 weighted images seems to be less important because only with T1 weighted images and flares, we already achieve reasonably good performance. Recall that our biceps model can directly generate the contrast enhancement map. This not only enables a more interpretable generation process, but also shows the potential of applying bicep to other tasks. For instance, here we show a maximum intensity projection rendering visualization of the contrast enhancement map generated from our model and also from the difference between a post-T1 image and a pre-contrast T1 image. On the left is the contrast enhancement map generated from pre to post experiment. We can see that major sinuses, including superior sagittal sinus, straight sinus, and transverse sinuses are clearly visible in the synthesized contrast enhancement map. The middle one shows the post to pre-contrast enhancement map. We can see that the contrast enhancement map generated from post to pre-experiment is very close to the real contrast enhancement map, which proves the potential of applying biceps model to tasks such as dural sinuses segmentation. In summary, we propose a bidirectional pre to post and post to pre-contrast MRI synthesis model in this work. Our proposed biceps model outperforms all current methods on an MS dataset. There are still limitations of our work. For instance, we need to further improve the synthesis results on the cerebellum region. In future works, we plan to test on other applications such as lesion segmentation using the synthetic image generated from our model. Thanks for listening. Any questions are welcome.